Hello everyone, we are Team Sustainable Environmental Solutions from University of Texas at Arlington. Today we will be presenting our proposal for SWANA Student Design Competition 2023. Our team members include Aishwarya, Doreen and myself Hussain. This presentation will go over introduction, problem statement, proposed scenarios, economic, environmental and social analysis of all the scenarios, discussion and then recommendation.
Methane is a potent greenhouse gas and is far worse than carbon dioxide due to its heat-trapping capacity. As of 2020, landfills are the third largest source of anthropogenic methane emissions in the United States, and it accounts for over 14.5% of the total emissions. As you can see in this waste management hierarchy of EPA, the treatment and disposal in the landfill is the least preferred waste management technique. And similarly, for the food recovery hierarchy, landfilling of the food waste is considered to be a least preferred option. We are assigned to determine the best organic waste management option for a county situated in the northwest region of the US, having a population of over 600,000 people. The county has a strong agricultural industry, and the waste generated is 37% of organics. Using the three types of sustainability, that is the economical, environment, as well as social aspects, we have to determine whether landfilling the organics and setting up an RNG plant, or using source separation, diverting the organic waste and setting up a composting is the better alternative. Several tools were employed for a detailed analysis. For methane estimation, we used EPA's Langer model as well as the IPCC model. For economic analysis, we used EPA's landfill gas energy cost model and values obtained from the current industrial ranges. For economic and social analysis, we used the power tool developed by UTA as well as the generally available rating and weighing tables. Four different scenarios were explored in the study. The first one was where an RNG power plant was constructed on the landfill where there was no organic diversion happening. And the second one was when RNG power plant with organic diversion starting from 2025. In both the scenarios, we looked at two cases. The first one by using methane emission estimates obtained from EPA's Langer model, and the second by using the emission output from the IPCC model. The third scenario included source separation and sending the organics to a composting facility. We explored two cases here. The first one was using a windrow composting, and second by using a covered aerated static while composting. The fourth scenario involved source separation with anaerobic digestion, where the organics were sent to the AD for energy production. We explored two cases here. The first one was by using an existing AD in the county, and the second one was building a brand new anaerobic digester in the county. 3 out of 4 scenarios explored in the study include source separation that involves separating the waste into different categories for separate collection. There are several opportunities involved in this. The first one is that it's a sustainable practice and it reduces the airspace consumption. Since the organics and recyclables are now diverted from the landfill's life is extended. And since moisture content is reduced, the chance of leachate production as well as chances of landfill settlement is reduced. The landfill gas production is also reduced in a large amount. The challenges mainly involves the behavioral shift that would be necessary for the public for source separation to be successful at an individual or a household level. In the past, US had segregated waste collection system, whereas it moved to a single bin waste collection in the past. Now, if source separation needs to be successful, the people have to go through another behavioral shift that is challenging. Lack of proper infrastructure and strategic planning is another challenge. The costs involved in setting up new bins, trucks, and transfer stations are also challenging. Let's now look into scenario 1 and 2 in details. It involves setting up an RNG plant in the landfill. RNG is basically the landfill gas that's getting collected and undergoing secondary treatment to form biogas, and further undergoing its advanced treatment to become RNG, which constitutes 96 to 98% of methane in it. Let us look at the advantages of setting up an RNG plant. It reduces air pollution and it offsets the use of non-renewable resources like petrol, coal, or diesels. It has tremendous health and safety benefits as it destroys air pollutants and VOCs during their advanced treatment phase. They generate revenue and job and benefit the community at large. It reduces the environmental complaints cost for the landfill owners as they are turning the pollution into a valuable community resource. It is incentivized, which is good economically, and they can be used in natural gas vehicles without changing any of its infrastructure or reducing the performance. There are several challenges involved in setting up an RNG plant on a landfill. The cost for processing LFG is typically higher than the cost of the natural gas price in the recent years. Although the renewable incentives could cover these, they have a quite complicated structures and these transactions are not universally available, and hence these credits can become volatile. A natural gas pipeline should be closely available for the project to be economical, otherwise the capex cost of the project would go high. And another challenge is the flow rate of the LFG in this landfill. If it is below 800 SCFM, in most cases, the project cannot be scaled and cannot be economical. They also have a potential to de-incentivize more sustainable waste management solutions like source separation or recycling because of these incentives available. The methane emissions from the landfills were estimated using EPS LANGEM as well as the IPCC model. The top two curves represents the EPA's LANGEM output, whereas these two curves represents the IPCC model. In the first scenario, that is when there is no organic waste diversion, the peaking occurred around the same time, that is around 2032 in both the outputs, and we can see that there's quite a difference in the emission quantity. LANGEM overestimates the emissions, and IPCC is more realistic to the real life scenario. In the second scenario, that is when there was organic waste diversion from 2025, we can see that the peak shifted to early 2024 in IPCC output, whereas the LANGEM showed that the peaking occurred around 2035, which is quite later. From this, we can clearly understand that the LANGEM is not considering the type or the composition of the waste and what waste is being diverted. And this is one of the major flaws of the LANGEM model. It ignores the waste composition and the temperature. It also considers the L0 and K value to be constant, which are not so in the real life scenario. The average RNG sale price was estimated using the RIN and the natural gas price trends over the last 3 years. The Henry Hub natural gas price plotted here for the last 3 years, we can see that the average value was around $3.72 per MMBTU, and the average RIN price was around $2.21. We know that 1 MMBTU accounts for 11.72 RINs, and hence the total RIN price was found to be $24.93. Upon adding the natural gas price as well as the RIN prices, the total estimated price for RNG was $29.66 per MMBTU. While running the LFG cost model for the economic analysis, we ran several scenarios, and we found that even with a distance of 10 miles to the natural gas pipeline, the model gave us a break-even period at year 2. And this was quite baffling. And we looked into the cost that's used in the model, and we found that the values were outdated. The capital cost that's used for these scenarios were almost half of what's currently being used in the industry. For our final analysis, values based on different projects done recently in USA by Vision RNG were used. The capital and operating costs were estimated based on the size of the RNG plant. For the LANGEM output, we used 1,500 SCFM capacity values, and for the IPCC case, we used the cost for 1,000 SCFM capacity throughout the analysis. While looking at the cost-benefit analysis for the scenario 1, that is without waste diversion, for the LANGEM output, we are getting a break-even at 2031, and the cost-benefit ratio is 1:1.43, making the project highly feasible. Whereas for the IPCC scenario, we are getting a break-even in the year 2034 with cost-benefit ratio 1:1. This is quite risky considering that in 2035, the landfill is getting closed. In our second scenario, where the organic waste is getting diverted from the landfill from 2025, in the case 1 with LANGEM, we are still seeing that the project is breaking even in 2031, and the cost to benefit ratio is 1:1.36, making the project highly feasible. However, for the IPCC, we see that the cost to benefit ratio is 1.6:1, and we do not see a break even in the life of the project, making the project not feasible. The following processes were considered within the boundary for the environmental analysis: the waste transport from the source, the pre-processing, screening, and compacting of the waste in the landfill, collection of the landfill gas as well as leachate and its processing, conversion of biogas into the RNG, and sending into the RNG pipeline or the end use. The table here summarizes the emission from an RNG plant on a landfill. We see that methane is the largest emission, followed by carbon dioxide and N2O. Although there are different stages, the direct emission accounts for most emissions.
In our third scenario, we will be looking at composting. Source separation is necessary for this scenario. Composting is a sustainable practice and it reduces GHG emissions and saves landfill space. It is less labor intensive and it also provides high quality soil amendments. However, some of the challenges associated with composting includes odor problem, pest problems. It can be time consuming, it can take a lot of space, and we also need to balance carbon to nitrogen ratio, the moisture level and the temperature for it to be more efficient. For our report, we compared windrow composting with covered aerated static pile composting. Each technology have their own advantages and disadvantages. However, we decided to move forward with CASP composting technology because it's much faster, it's more efficient, it produces less odors and also reduces GHG emissions. Food, yard and animal waste will be diverted from landfill to the composting facility. We are assuming that the facility will start working in 2025 and every year more of the organic waste will be diverted from landfill to the facility. We are assuming that the facility will get 100% diversion by year 2029. To estimate the area needed for active composting, we looked at many important parameters. The figure here provides the dimensions that we selected for our pile, and rest of the important parameters are shown in the table. Table on this slide shows the parameters that we looked at to estimate an overall area needed for the composting facility, and the figure here shows the initial layout for our composting facility. We have estimated that an area of around 6 acres will be needed for this composting facility. For our economic analysis, we reached out to a few people from the industry and we also conducted a literature review. We estimated the capital cost to be around $20.5 million and the operational cost to be around $765,000. The graph here shows the cost to benefit analysis of the composting facility. We have estimated the break-even to occur in year 2042, and we also estimated that the facility will last for 50 years. Figure here shows the boundaries that we used to estimate the emissions from the composting facility. We looked at the emissions from the waste transportation, the shredding of the waste, the depackaging and pre-processing of the waste. We also looked at the emissions from the composting facility itself and the post-processing and the use phase. The table here shows the estimated emissions for criteria pollutants and greenhouse gases for this facility. We see that the direct CO2 emissions from the composting itself are the highest, which is followed by the emissions from waste transportation.
The fourth scenario our team decided to explore is anaerobic digestion, which is basically the breakdown of organic matter in the absence of oxygen to produce biogas and digest it. Advantages of AD includes production of renewable energy, diversion of waste from landfill, creating landfill space, and also reducing greenhouse gas emissions. It produces digestate, which can be used for fertilizer. Its challenges include process complexities, high capital costs, it's energy intensive and may generate unpleasant odor and noise. Power tool was used to estimate cost and emissions for AD. It was developed in UTA and funded by CTED and US DOT and was also used for an EPA project. The assumptions used for Power Tool are listed in the tables as shown on the slide. We used Power Tool to estimate the cost for AD, and we had capital costs coming up about $36 million, with operational costs about $760,000. This graph shows the cost-benefit analysis of AD, and our break-even point was achieved in the year 2042. This project was assumed for a lifespan of 50 years. For environmental analysis, the figure above shows the boundaries we considered for our emissions from transportation, pre-processing, post-processing, and end of use. And the table below shows the estimated emissions from greenhouse gases and criteria pollutants. For social analysis, some important things that we considered are involving a community, engaging them in the whole project by sensitizing them through awareness program, and also creating incentives as a way to motivate them to fully participate. For our social analysis, we use these 3 life cycle phases: construction, use, and end-of-life phase. We assigned weightage to each question listed below, and based on the impact of each technology, scores were assigned. And based on this scoring, AD got the highest, with composting scoring the least.
In this presentation, we have looked at 4 different scenarios with 3 different technologies. Coming towards the RNG plant, we have 2 different stories. First, if we decide to go ahead with the methane estimated values from LandGem, we see that our project is economically feasible with good cost to benefit ratio, and the break even occurring in 7 years for both cases with and without source separation. However, if we decide to go ahead with the methane estimated values from IPCC model, we see that our projects are not economically feasible for both with and without source separation. Our capital costs range from $23 million to $28 million based on the size and capacity of the plant, and the operational and maintenance costs are around $2.5 to $3 million. Coming towards composting and anaerobic digestion, we see that AD has the highest cost to benefit ratio with 1 to 3.3, whereas composting comes in second and RNG plant in all the scenarios come in the last. The break-even point, however, is the longest for AD, occurring in 18 years, and for composting it results in 17 years, and for RNG plant it depends on which values we are using and what scenario we are going forward with. The AD has the highest capital cost with $36 million, followed by capital cost for RNG plant, and the capital cost for the composting comes at the end. Our operational and maintenance cost for AD are $759,000, whereas composting it's $807,000. When comparing the emissions from all 3 technologies that we looked at in this project, we see that landfill produces the highest amount of emissions for carbon dioxide, methane, VOCs, nitrous oxide, and PM2.5. Composting also produces the highest emissions for NOx and PM10. Composting results in the lowest emissions for VOCs and nitrous oxide. Coming towards anaerobic digestion, we see that it shows the best performance when it comes to emissions. It produces the lowest emissions for carbon dioxide, methane, PM2.5, and PM10. Community involvement is very important for this project. 3 out of the 4 scenarios that we looked at involved source separation, and we believe that source separation is not possible without the involvement of the community. Also, each technology has its own pros and cons. Each technology have different impacts during construction, use, and end phase. Therefore, we need to sit with the locals and we need to let them know what they're looking at for each technology, and we need to ask them questions what works best for them, and we need to involve them in every decision. For example, do they prefer to drop off their waste by themselves to get some credits, or they want their waste to be picked up? Do we need to provide them the bins for source separation, or can they buy the bins by themselves? Therefore, we think that the strong involvement of the community is the key for the success of this project. Based on our economic, environmental, and social analysis, we found anaerobic digestion and composting to be more favorable when compared with installation of the RNG plant on the existing landfill. We can see that cost-to-benefit ratio for AD is the highest, followed by composting, whereas the RNG plant does not seem feasible when we look at the methane estimated values from IPCC waste model. Also, AD and composting produces relatively lower emissions. Therefore, we propose to install a pilot study for both composting and anaerobic digestion, and possibly see a hybrid system where the food waste can be sent to the anaerobic digester, whereas the green waste and the AD digestate can be sent to the composting facility. We would like to thank everyone for being here, and we are happy to answer all the questions.